Okay, so here's the question or statement. So we have sodium phosphate and lead 2 nitrate solutions react. Predict the products. Write the conventional equation, total ionic equation, and net ionic equations if there is a reaction. Okay.
Mm-hmm.
So the first thing that we want to do is we want to know a little bit about sodium phosphate. So what is the chemical formula for sodium phosphate?
If I'm not wrong, isn't it Na3PO4?
Okay, so you said.
Wait, no. NaPO4, I think.
It's just NaPO4?
I don't remember.
Come on, you got this. Anybody want to help her out? Is it just NaPO4?
Na2, wait, no.
Come on, you have all of these beautiful things that were in that packet that's on that. That should be able to help you out with that. What is the charge on phosphate?
-3.
-3. So then how many sodiums am I going to need to balance it out?
Wait.
So if we have a phosphate is PO4, can you guys see my writing up here? 3 negative. How many sodiums? What is the charge on sodium?
+1.
That's right. It's a +1.
Wait, so it would
Na
be
plus
3.
1, right? So it always has to be balanced out. If it's a chemical compound, it's going to balance each other out. If it says it's an ion, that's different. That means that it would be an ionic charge associated with that. Now, these are chemical compounds, so they're going to balance each other out. So how many do I need to balance it out?
So it is 3.
It is 3. You're right the first time. Go with your gut. Okay. Is it a solid, liquid, or gas? Jeff, solid, liquid, or gas? Or aqueous?
Oh, can you say that again? Sorry, I was doing something.
Is it
You
a
said
solid, liquid, or gas, or aqueous?
What, NaPO4?
Yep.
I think that's a aqueous.
That's correct. Now you guys need to know the states. You don't know the states, it's going to bite you in the butt. Okay, so lead 3 nitrate. What does that look like?
PB.
PB?
Wait, parentheses. NO3. Is it 2 or 3?
Three, right?
Was that?
3. Right.
3. That's right.
Okay.
Okay, solid, liquid, gas, or aqueous. So why is it 3? First off, before we get to that solid, liquid, gas, or aqueous, why is it 3? Why do we need 3 of them?
Lead 3.
Because it's lead 3. So that means it's lead plus 3. So we need 3 nitrates, which has a -1 charge, 3 of them to balance out that 3 plus. Make sense?
Yeah. What? Oh, okay, so when they put like lead 3 nitrate, you don't put a 3 next to PB?
No, that's just letting you know that the PB really is, it's PB 3 plus charge. 3 lets you know the charge on it. Okay?
Okay.
Okay, so that means that it's lost 3 electrons. So you need to find 3 electrons to kind of balance it out. And you're going to get that from the nitrates because the nitrates have nitrate. Yeah.
I see what you're saying.
Okay.
Okay, so like if to say it wasn't balanced, then it would say it was like 2 PB,
Yep. If it was lead 2, is that what you're saying?
Or yes, yeah,
Yeah. So if it's lead 2, that means it would have a +2 charge.
yeah.
Okay.
Okay, and then instead we would put, and then instead we would put NO3 2.
That's right.
Okay.
Yep.
Appreciate
Yeah.
it.
Okay. So you guys want to pay attention to that. So the Roman numeral always means the charge on that it could be that molecule or that particular ion. Okay.
I think that's what I got messed up on one of them, because there was a question that had, it was like, what are the name of the compounds like ZnCO3, and then I
Mhm.
put the 2 when
Okay, but
when
you
I
got to
said I was
remember
changing.
there are ones that are exceptions, right? And I've talked to you about that. One of the exceptions is zinc. Zinc is an exception. Zinc 2 is the normal. So if you just see zinc, let's say zinc phosphate, that usually means it's zinc 2 phosphate. If you see
Okay,
if you
it
see,
doesn't need to have that written out.
no, there's only a few exceptions. Everything else should have it written out. So
Okay.
silver, if you look back at your notes, silver is an exception.
Uh-huh.
So if you just see silver, Ag,
Yeah.
so silver, if it's just written silver chloride, right? That means it's
Uh-huh.
Ag plus, right? It's always going to be that one. If you just see silver chloride, but if it's something different, let's say it's silver 2 chloride, that means it has a +2 charge. So, but scientists, okay, so how the best way of saying it? You guys, you know how we use slang, right?
Yeah.
Because, I call you bro, right? Bro is short
Yeah.
for what?
Brother.
Brother, right? So, and even though we're not blood brothers, you're not my brother, are you?
No.
Right? So when I call you bro, you know that I'm referring to you as a term of friendship and endearment, right?
Yeah.
What's up, bro? Unless I come up to you like, what's up, bro? Or something like that, right? That's a little different, right?
You're pressing me about it.
Yeah. So scientists do the same thing, right? And so instead of saying silver 1, right, we just get lazy and we just say silver, right? Instead of saying silver 1,
Okay.
And so anytime that you just see silver, it always means it's silver 1. Anytime that you just see, so we'll say silver phosphate, right?
Yeah.
So that means silver 1 phosphate. That's what it really means. But we're scientists, we're lazy, right? So, and it's true, we're all kind of lazy, right? A little bit lazy, so we get lazy with that terminology, okay? So there are certain ones that we know, we kind of like as scientists, oh yeah, silver, oh, you mean silver 1, right?
Yeah.
And if we say zinc, we mean zinc 2.
Zinc 2. Okay.
Yeah, zinc phosphate, that means zinc 2 phosphate. So that would be Zn 2 plus. But those are exceptions. So all your other transitional metals, remember, transitional metals are going to have the Roman numerals.
Okay.
So,
yeah.
Okay.
That's what stumped me. Because I know I know most of the transitional metals need a Roman numeral to give them
Yep.
the charge, but yeah, that's the one that stumped me. So I appreciate it.
And I put that on there because it lets me know how well students pay attention to what I say. They're just, gotcha.
Yeah, I got the broad. I didn't get that little small detail. So I'm glad you put that in.
Yeah. Okay, so now we got this, right? We got this down. We got the first part. So what type of reaction is this? Anyone, the type of reaction.
Was a single replacement?
Is it a single replacement?
Probably not.
Double replacement?
It's a double replacement reaction, or what I like to refer to as a swingers reaction. You guys know what swingers are, right?
Yes.
Okay. You're telling me only one person knows that. Okay. So let me explain what a swinger is for you youngins who don't know that. A swinger is somebody they partner up. There's a couple, and then another couple comes along, and then they switch partners.
Oh.
Okay. So that's what swingers are. Okay. So double replacement is a swingers reaction, right? And so basically you're going to be switching partners. Now your cation, what is a cation again?
Positive charge.
Positive charge. So cation is going to replace a cation, and anion is going to replace an anion. So sodium is going to hook up with nitrate, and lead is going to hook up with phosphate.
So cation just replaces a cation and an anion replaces an ion.
That's right. And that makes sense, right? You're not going to sit there and put two negatives together, because what if it happens when you put two negatives together in real life?
Nothing.
Nothing happens?
No, I'm just kidding.
Two negative charges on the magnet. What happens?
They repel.
They repel, right? So they're not going to go together, right? Because this is all based on charge. You need that positive and that negative to hook up, right?
Yeah.
It's kind of like, kind of like what you guys do. Are you going to sit there, Vanessa? So I consider you a positive person. Am I wrong? You can let me know if I'm wrong.
You're not wrong.
I'm not wrong? Okay, so you're a positive person, right?
Yes.
And so two positive people coming together, right?
Mhm.
They're not going to get along, right? Because you need that positive to kind of bounce off that negative.
Yeah.
Two happy, cheerful people, it would be crazy. You'd hate each other, right?
Yeah.
You'd last about a week, right? So
Yeah.
it's the same concept. So you need that balance, that good and that bad. They have to come together to balance each other out,
Okay.
Okay. So in this case, so we're going to get what are going to be our products.
NaNO3.
NaNO3. Is the charges balanced here? We have a +1 and a -1.
So yeah.
Okay.
Wait, this is where I get confused because the Na has a 3, so what happens to that?
We worry about that at the end. That's what we do. We use those coefficients to sit there and adjust that.
Oh, okay.
Okay. And what is the other product?
PbPO4, and the charges are okay.
Okay. God, that just worked out perfectly, didn't it?
Yeah.
Okay, so now that we have everything balanced, right? So it's perfectly balanced. There's no extra charge on anything like that. So the charges are a total of 0 on both of the compounds, right? So now we sit there and we go through and balance the equations. Now we use coefficients to balance the equations, okay? So how many sodiums do we have?
Don't we need the states?
Yeah, we do. Well, I'm saving that for later, for a second, because that's going to take us a little bit to another level.
Okay.
Okay, so just work with me on balancing it first, and then we'll work on the states. So how many sodiums do we have on the reactant side?
3.
So we have 3. We have 3 sodiums. How many on the product side?
1.
Okay. How many nitrates do we have on the?
Oh, we have 9.
We have 9 nitrates.
Right?
Three.
Oh wait, no, the 3 doesn't. It's 3.
We have 3. And how many do we have on the product side?
3. 1. Wait.
Okay, we have 1. That's right.
Yeah.
Well, we need 3, right? That's where you're just getting ahead of yourself. Okay, and then lead. How many lead do we have on the reactant side?
1.
And on the product side?
1.
And phosphates?
1 and 1.
Okay. Okay, so the phosphates were good, right? So we have, those guys are balanced. So what do we need to do? What coefficient do we need to put in front of the sodium nitrate so that we'd be balanced? On
3.
Okay, so then that gives me 3, 3. So everything is balanced. Simple?
Yeah.
Okay, so let's talk about the states now, right? So can you guys see my screen? You guys have this? Do you guys print it out? Because you're gonna need it for your exam.
Yeah.
I don't have it with me though.
You don't have it with you? Slacker.
No, because I've
What, are you at your boo's house?
no.
Okay, so let's talk about how to use that. So I need somebody to do me a favor, write down our conventional equation right now, our balanced conventional equation while I flip it up over to a slide. Okay, is that cool? Who's gonna do that? Who's gonna be responsible?
I can do it.
Okay, you got it? So that we can
Yeah.
put this up once I show you my
Yeah.
slide. Let me see. I may not be able to show you. Struggles. Let's see. Do I have everything? No, I don't. I had to get another computer, so the campus gave me another computer, and I'm learning about it here. It's doing its own thing. Let's see. And it's not doing what I want it to do. Give me 1 second while I figure this out. And do chapter 9. There we go. Oop, wrong chapter 9. Eight. Yeah, but it did open up. There we go. Okay. Come on. Let's see. Can you see my screen?
Yes.
Okay, good. So you definitely want to sit there and print that out, because I guarantee you're going to have a couple of questions that deal with this solubility. Okay.
Okay.
Now we have two products that we're making. So what was one of our products?
Sodium nitrate.
Sodium nitrate. So we have NaNO3. And then what was the other one?
Lead phosphate.
PB. Lead what? Which lead?
3.
Lead 3. Okay. Okay. So although I was bad, gave you guys lead 3 instead of lead. Okay. So let's go. Okay, so we want sodium, which would be the next slide. I'll do a better job this time. So lead 3 acts just like lead 2, okay, in terms of solubility. So we could say lead 3 is going to behave the same way, even though it's not on the table. Okay, so what we want to do is go, you said lead phosphate. Lead phosphate, so you go over to lead phosphate, and it says it's nearly insoluble. What does that mean?
It's a solid.
It's a solid. So we know that that's going to be a solid. And then we have sodium nitrate. Sodium nitrate, it says soluble. What does that mean?
Aqueous.
It's aqueous. Okay, you see how to use the table?
Yeah.
Yes.
Piece of cake, right? Simple. It's just like, oh. Ryan, are you with me?
Yeah.
Yeah. You're like, it's early in the morning. Barely, but I'm here. Okay, so let's see. You share. Let's go back. Okay, so you didn't lose it. Good. Okay, so I'm going to erase this stuff down here, and then I'm going to put the states. I'm going to erase this, since we know what it is. Okay, so we know our states are going to be, you said aqueous and a solid. Okay, simple so far?
Yeah.
Okay, so that is our conventional equation. Okay, so now we're going to do our total ionic equation. Okay, so your total ionic equation only works with ions. So your ions are going to separate. So in the case of anything that has aqueous, it can separate into its ionic components.
Oh, but solid, liquid, and gas can't. They stay the same.
That is correct, right? So that's why we call it the total ionic equation, right? Okay, so this first one, what is it going to separate into? The sodium phosphate.
3 sodium with a +1 charge.
Okay, you're going to separate into 3 sodium, right? Because you no longer have that plus and minus interaction to kind of keep them all together. So each sodium isn't going to act independently. Okay, so that's why you have that coefficient of 3 in front. Okay, now what else will we have?
PO4 with a -3 charge.
Okay. Stacey, you're doing the heavy lifting here. Class is just like, we're gonna let Stacey do it because Stacey knows what she's doing.
PB. Plus. Wait, it has a +3 charge.
There we go. So 3 plus, okay. Solid, liquid, gas, or aqueous?
Aqueous.
That's right.
And then NO3 with the negative charge. Aqueous.
And how many of them do we have?
1.
How many do we have?
Oh, 3.
Okay. And we're making this guy here.
Sodium with a +1 charge.
We have 3 sodiums with a positive charge. And
3 nitrate with a negative charge.
am I done?
No.
What else do I need?
Was
Oops.
PB with a +3 charge.
Is it PB?
Wait, no, that one stays the same.
That's right. Let's see. Okay, let's see. That's right. Because it's a solid.
Mm-hmm.
Okay, so have you guys ever went to a party with somebody who doesn't want to do anything at the party? They don't talk to you or anything like that. They just take you to the party, right? And they just watch everybody else talk and interact. Have you ever been with anybody like that or seen anybody like that at a party?
Yeah.
Okay, so those people are called spectators, right? They come there to spectate. They just come there to watch, right? So they're not really doing anything in the reaction. So they're like deadbeats in a sense, right? They're not doing anything. They're not interacting with anybody. They're not trying to hook up or get numbers or anything like that. So they're kind of, they're just there, right? So there are chemicals that are going to be exactly the same way, right? Those are spectators. So we want to identify the spectators. The spectators are going to look exactly the same on both sides of the equations. Exactly. Have to have exactly the same charge. Okay? So, who are our spectators?
3 Na.
Mhm.
3 No.
3 NO.
And I think that's all.
Okay, so for our net ionic equation, we get rid of the spectators because they're dead weight, right? All they did was bring the person to the party. They didn't do anything else. So
Mhm.
net ionic equation. So we have PB. Oops, that should be 3 plus. I don't know what happened to my, oh, I see. It moved. Okay, so that should be PB 3 plus. BO4 3 minus. That's it. Pretty simple, not too
Yeah.
hard. So the hardest thing, and it's weird, it goes back to what I kept telling you, why we spent so much time on nomenclature. Hardest thing is nomenclature, right?
Mhm.
Naming what you're starting off with, because if you get that wrong, everything else goes to hell in a handbasket after that. Okay, so you want to make sure that you're strong in nomenclature. You got that, Fabiola?
Yeah.
Okay. Any questions, Ashley? You have any questions?
No, I understand this pretty well.
Okay, good. Okay, any other questions? Anybody have any other questions? Okay, I have a question for you, right? Let's say we have, let's say we have this guy. So instead of lead 3, we have, let me get my annotate on. So we have sodium phosphate instead of lead 3, we have potassium nitrate. Okay, so if I have potassium nitrate, and I'm going to change my chemical equation now to, so what is the charge on potassium?
+1.
So +1. So this is going to change. And this is going to change. Just going to go ahead and balance it for you, if you don't mind. Okay. Okay, so if we go to our table, okay, switch. Go to our table. So we have potassium phosphate. It says it's soluble, right? So what does that mean for our equation?
So there's no solid, it's all aqueous.
Everything is aqueous, exactly. So let's go back to my whiteboard. Hopefully it's still there. Yeah. Okay, so then now, in this case, we have no solid. This is also aqueous. So we get K plus AQ. And there's 3 of them. Plus PO4. 3 minus AQ. So how does that change my net ionic equation?
You cancel out PO43 and you're only left with lead and potassium.
Oh, sorry. There's no lead anymore.
Oh,
Sorry. Let me get rid of that. Now we just have potassium. Okay, now
everything cancels each other out?
everything cancels each other out. So this case, it's not going to be a reaction. Nothing is going to react. So you're not going to see anything. The solution is going to stay clear. Nothing is going to happen. So you're just going to write NR. So you just write this guy in NR. Simple?
Yeah.
Okay, so all of your exam is either multiple guess or matching. Okay, so it shouldn't be too hard.
I got a question. I don't know if you already went over this, but if you did, I don't remember.
Go ahead and ask.
Are we still gonna upload our work, or like if you
No.
know? Okay.
No. So for your final, it's just you're going to get your score at the end. You'll know exactly what you got on the final.
All right.
Okay.
All right.
Any other questions?
Can you go over electrostatic forces really quickly?
Sure. Okay, so when we talk about electrostatic forces, we're talking about basically the forces that are going to be exerted because of electrons, right? So if you have something that is positive, what's going to happen when you bring it together?
They repel.
They're going to repel each other. So this guy's going to go this direction, this guy's going to go in this direction, okay? So what if I bring a positive and a negative together?
They're going to go with each other?
They're going to come together. They're going to hook up, right? They're going to stay together, okay? If I have two negatives,
They repel.
they're going to repel as well. Simple?
Yeah.
Yeah.
That's it. Any other questions? Okay, there's no other questions. Good luck.
Wait, I got one.
Okay.
Can you go over a little bit about the last lecture, the one that you recorded?
Yes.
Thank you.
Everything stems from PV equals nRT. What is P?
Pressure?
Okay, That's correct. P equals pressure. B,
Is it volume?
volume. T,
Temperature?
N,
Is it the amount?
number of moles. That's right. And R.
Mm. Force? No.
Anyone? Anyone? I'll tell you. It's the universal gas constant.
Oh, okay.
Or we'll call it, if I can spell, oops, or the ideal gas constant. You'll see them written both ways. Okay, so this is a constant. Do you guys know what a constant is? If someone is a constant in your life, they're what?
Me, I'm sorry, what did you ask?
I said, if someone is a constant in your life, they're what?
Like the same?
The same, right? So constant is the same, okay? So the ideal gas constant has a specific value if you use the right units. So it's 0.0821. And the units are, it's going to be ATM times liters divided by moles Kelvin. You guys remember what a Kelvin is, right?
Yeah.
Okay. So you always want to put your units when you're dealing with temperature in Kelvin to use your equation. So you always want to convert it to Kelvin. Okay. So PV equals nRT, right? That's the equation that we're going to, everything that we're working with stem from. So if we have a situation where, let's say, we have the number of moles are a constant. Meaning that they're not changing, they're not mentioned at all in the question. So then we'll just use PV is going to equal, instead of saying, now you're saying it's a constant, so we're going to use K as our constant, T. So we're setting this up so it'll all be one constant. So in this case, you have PV over T equals K. So if I say I have one pressure, one temperature, and I have another pressure and another temperature, I'm able to calculate the volume that's going to be changing. So then I get this equation when moles are constant. So I can use PV over T is equal to P1 V1 over T1 is equal to P2 V2 over T2. Now I can do the same thing if I have, let's say, moles and temperature are constant. So then in that case, I get P1 V1 equals P2 V2. Now, if I say that moles and volume are constant, I know this is a quick overview. Then I can use P1 over T1 equals P2 over T2. Okay, so I'm going to give you, from the ideal gas law, we can get all of the other gas laws. These are examples of all of the different gas laws that we have. We can also say the same thing with pressure being constant and all that stuff. So let's say we have a question that says, let me see, in a expanding cylinder at constant temperature and pressure, temperature and temperature and pressure. Okay, so here this is basically telling us that we have constant temperature and pressure. So we're not going to worry about temperature and pressure. All we're going to be worrying about is volume and moles. So in that case, we're going to have this equation. V1 over N1 equals V2 over N2. Okay, so our V1 is going to equal what?
Two liters?
You mean 1 liter, right?
Oh, yeah. I wrote it wrong.
Okay, our N1 is going to equal
5 mole?
our N2 is going to equal
15 moles.
So then our V2 is what we're looking for. So we solve for V2. And then we just plug it in, plug and chug. V2 is going to equal what? So it's 1 liter times 15 moles divided by 5 moles. So moles are going to cancel out, and we're going to be left with 3 liters. Simple?
Yeah.
So the ideal gas law kind of helps us to go between all of the different gas laws. It allows us to set up those equivalencies, right? So sometimes we can just use the ideal gas law. If we're given P, V, N, and we're looking to solve for T. So if we're given the pressure, the volume, and the number of moles, we can calculate the temperature of that particular gas. Do you want to try one of those?
Yes.
Okay, so let's say we have let's go. Let's say we have 4.0 grams of helium is put in a 0.5 liter container at a pressure of 1.30 atm. What would be the temperature? Okay. So I'm gonna erase this question down here. Everybody got this one down here?
Yeah.
So then we'll move this one. Okay. So in this case, I hate the fact that it doesn't wrap for me. Okay. So in this case, we're just going to use the PV equals nRT, right? So, but we need number of moles. How do we calculate the number of moles if we're given 4.0 grams of helium?
Molar mass.
Molar mass. So what is the molar mass of helium?
Four.
Ooh, that's convenient. So 4 grams of helium for 1 mole. So I have 1 mole, right? Okay, so this is going to be my number of moles. So that's going to be my N. What is my V?
The
0.500 liters.
0.500 liters. What is my, that should be ATM, not, there we go. My pressure.
1.30. ATM.
Okay, so if I plug it in there, plug and chug, and I solve for T, I get T equals PV over NR. So then I just plug everything in. We know what R is. R is 0.0821, right? So then we have 1.30 atm times 0.50 liters divided by 1 mole. That should be 1.0 times 0.0821, and that's ATM liters over mole Kelvin. So then moles are going to cancel. ATM is going to cancel. Liter is going to cancel. And so we have inversed. So our unit should be just Kelvin. Okay, what do you guys get?
Is it 7.9 or did I do it wrong?
Boy, that is really cold. 7.9 Kelvin. Okay, piece of cake?
Kind of.
Kinda.
So what I always recommend, I always write them down. I write down all my givens. Okay, this is given me, this is given to me, this is given to me. By doing that, it kind of sets you up to figure out what you need. So if you have a V1 and a T1, and then you have a V2, and so you know you need to solve for a T2. But then you just modify your equation so that you're working with V's and T's, right? So if it's V's and T's, that means they're going to be on the same side of each other. It's going to be V over T, right? And so V1 over T1. So if you have P's and V's, then they're going to be P times V. So P1 times V1. Are you with me?
Yes.
Yeah.
Yeah.
And that's the best way of doing it, because then you just, it's a checklist, you know, check, you know.
Mm-hmm.
Okay. Any other questions? And you have a lot of practice problems on your homework. That's also due Friday.
Hmm.
Okay. Okay. Well, I have nothing else. If you guys don't have any other questions, I will wish you luck. The tutors will be having review sessions, so hit them up. They're going to be about an hour.
I got a question actually.
Yes.
So there's a problem for homework. What was it? Homework 10 or
Okay.
yeah.
wanna
I
share
did
your-
it all times and I got it wrong and I kept getting wrong. So I just have a question on like what I did wrong.
Okay, so let's pull up that question. It says, write the complete ionic equation for the reaction when AuBr Okay, so I can tell you what you did wrong, right?
Okay, yeah.
So Au
Uh-huh.
isn't going to form a solid. So gold does not form a solid with nitrates. Nitrates don't form solid with anyone. Okay, so it's all going to be aqueous. So then you're going to write NR.
Okay.
There's not going to be a reaction.
Okay.
And that's it.
Okay. Wow. Okay.
Yeah. So what I'll do, I'll give you a couple more tries on that one. Give me 1 second so you can fix that. So there are going to be a couple of them that are like that. Anytime that you see nitrate, nitrate will never form a solid.
Let me write that down.
Okay. So give me Chem 101. Let's give you guys a couple more attempts on that one. So that is homework number 10. Is that correct?
Yes.
Edit, throw in, give you guys another 3 more attempts. Come on. Okay.
I also had a hard time with this one.
Okay. First off, H2, is that ever going to be aqueous?
No.
No. What is it going to be?
Is gas?
That's right. It's going to be a gas.
Okay. I don't know why I put aqueous.
And it's funny because it's always those little things that get you, right? It's just like,
Okay. Yes, I think that's it for this one. So for the acids, I know you were talking about how like there's like strong acids or something
and
like
weak
that.
acids. Yep.
Yeah, weak acids. How do you identify them? Like, how do you know which one's strong and which one's weak?
Anything that has OUS is going to be a weak acid.
OUS, weak.
So
Okay.
sulfurious acid, right?
Mhm.
Anything that has IC is going to be a strong acid unless it has a carbon in it. Anytime an acid has a carbon in it, like acetic acid has a carbon in it, it's going to be a weak acid. So for instance, sulfuric acid is a strong acid. Hydrochloric acid is a strong acid. Now, hydrofluoric acid is a special, it's very special. That one is going to be a weak acid because it doesn't want to separate at all. And so the way that you really determine is whether it forms an ion. If it forms more ions than the acid molecule together, then it's yeah.
Oh, okay.
Okay. Does that help?
Yeah, it does.
Okay. Okay. Any other questions? Okay.
Is it the same thing for electrolytes? Like the strong electrolytes are the
Exactly. They form strong electrolytes, forms ions, where weak electrolytes want to stay together.
Oh, okay.
Okay.
Got it.
Yeah.
Let me check my other homeworks and see if I. So since I got this one wrong, can you help me with this one?
Sure. It says, what is the mass in grams of carbon dioxide that can be produced from the combustion of 2.76 moles of butane according to the equation? 2 butane plus 13 oxygen yields 8 carbon dioxide and 10 water. Okay, so we're given, let me see. Do you mind if I write on your board, on your screen?
Yeah.
Okay. So we're given the number of moles of butane. So we have 2.76 moles of butane. Okay, so I'm already in number of moles, right? So I have quantity already. So I can use my chemical equation. So what is the relationship between butane and carbon dioxide? For every number of butane, I have how many carbon dioxide?
One?
No, because here, what is this? This says 2.
Oh, 2C4.
Yeah, 2 Cu4 for every 8. So you want to use the stoichiometric, right? So the whole purpose of having a balanced equation is so that you can use it to calculate everything else. So it's kind of like that recipe, right? So if you're making 5 cakes, right? You're not going to buy 1 box of cake, are you?
No.
Yeah, you know you need to make 5, right? And you
Yeah.
know that for every cake box that you make, you need 3 eggs, right? So
Yeah.
if you're making 5 cakes, are you going to just bring 3 eggs?
No.
No, so you're going to have to scale up appropriately. The way you do that is by using that recipe. So you know that you have 2.76 moles of butane. So you use our chemical equation for every 2 moles of butane, we have 8 moles of carbon dioxide. Okay, so that means moles cancels out. So now I have moles of carbon dioxide. So how do I go from moles to mass?
That's a good question.
So mass is in what units?
Grams?
Grams. So how do I go from moles to grams?
Do you
Look
use
at
that
the
one
units.
number? It's like starts with an A. The A. It sounds like
Atomic mass, yeah, or you could say molar mass, right?
Okay. Yeah.
Yeah, so we need our molar mass. And where do we get that from?
Periodic table.
Periodic table. So how many carbons do we have?
One,
And CO2, 1. How many oxygens?
2,
Okay, carbon weighs what?
12,
Oxygen weighs
16.
2 times 16. That's 32. So what? Add them together. 44 grams per mole. Okay, so all it is really, if you think about it, it's applying everything that you've learned. You've talked about moles. You're converting moles to mass. You use molar mass, you know. So in that case, your moles are going to cancel out, and then you're going to be left with grams. How many sig figs should you have?
2?
2?
No.
Because remember, your coefficients don't count towards your sig figs, because those are exact numbers.
Oh, so there are 3?
That's right, 3. Okay.
Let me do the math now. I got 485.76.
You said 485?
0.76. I don't know if I'm doing it wrong.
No, I'm not saying that you got it wrong. That seems about right. So if you have 4 times 44 times 2.76, 485.76. So 3 sig figs, so it'd be 486, right?
Yeah.
Yep, that 2.5 is way off, right?
Yeah. I don't know how I got that.
Yeah. Okay, so remember that. So always remember that you're going to use stoichiometry. So if you're given let's say you're given a reactant and they want you to figure out a product, you have to use your balanced chemical equation to get there, right? So we're given the reactant, we're finding our product.
Yeah, it's just these are hard because it's like any little thing, if you do wrong, it's like it already messes up your whole answer.
That's right. Yeah. Well, see, but that's the important part of that chemical equation. You want to make sure that you got that one right, because if that's wrong, then that throws everything else off.
Yeah.